Sure. And it's a real pleasure to have a computer vision scientist here. We haven't had enough over the years. And we're very lucky to have Deva Ramanan here, recently of UC Irvine and now just moving into a new place at Carnegie Mellon University. And we're lucky enough to get him to come here. Those of us who know vision know that he's been very prolific over the years. He's still a young researcher. I think he's won a Young Researcher Award in 2012. But he's done several contributions. We read his papers a lot in the vision group. You're involved in the deformable parts models, and then something that's dear to my heart, pose estimation work using the flexible model of parts. He's done many different things, including he's won the Mark Prize in 2009, which is for young researchers, right? Early career researchers. But the same year, the next year, he won the Lifetime Achievement Prize for the Pascal Visual Object Challenge. So his life is moving quickly. Very good. He's a PAMI Young Researcher Award, and the one I like best is the Popular Sciences Brilliant 10 Researchers in 2012. So those of you who are out in the audience, this is not about dinosaurs. The long tail is about distribution. So I'll let Deva talk about introduce us to the material. Thank you.
Thank you very much. It's a thrill to be here. Thanks for the gracious introduction and the invitation to come out. So I'll talk about a bunch of work that I've really done over at Irvine, and so I've listed a bunch of students and colleagues that have really done all the grunt work here. So let's kind of set the stage for the discussion, hopefully, that we'll have. Oh, and let me also say that I'm really happy and would love to entertain questions during the talk. I'll also pause at certain points to ask if there's any questions, but feel free to interrupt me with comments, suggestions, etc. As we go through stuff. Okay, so just to kind of get ourselves on the same contextual page, what I'm personally interested in, and I guess what our lab works on, is what I would call visual understanding as opposed to pattern classification. So there's a really kind of aggressive tendency to reduce vision to a classification problem, where if you want to find out is there a person here or not, you could phrase this as a binary classification task, you want to answer the question with a yes or no. But particularly what I'm interested in is, I think very close to what Jim mentioned as well, more detailed explanations and descriptions of what's going on in an image and video. So here, it's not just that there's a yes-no answer to is there a person here. There's two people. They're interacting with each other. They have 3D pose. They're interacting with objects. And so there's a lot of rich stuff going on. And so I'm interested in and would like to build automated algorithms that can produce this kind of output, in addition to ultimately even this kind of output, a 3D understanding. Okay. All right. And so what I wanted to do in terms of structuring this talk was the first part of it was I wanted to try to give a little sense about why I think this problem is hard. And then in the second and third bits, give some approaches that I think are seem like potential solutions for this, or at least ones that we're pursuing locally at our lab. All right, so first off, why is it hard to really produce this rich visual description of what's happening in an image or a video? And in order to kind of dig into that question a little bit, let's focus concretely on a specific problem that personally I've worked on for a long time, and that's how do you find people in images? So for the moment, pretend the task is given an input image reporting back these red boxes that surround every pedestrian or person in the image. So how would we build an automated system for doing this? So back in the, I guess, more of the early days of vision, I would imagine that we would take an approach that'd be very model-based. We would argue that, okay, let's try to build a model of what a person looks like, and maybe we can model a person as a collection of cylinders, an upper body cylinder, a lower arm cylinder, and we can model how those cylinders can move around, and that would capture the variation in pose. And about 10 years ago, I would say that our field transitioned to a much more statistical perspective on things, where if we want to build a pedestrian detector, what we do now is we don't really build models, we collect data. And we'll argue about what, hopefully I'll give you some intuition about what's good and bad about this data-driven view of things. But nonetheless, if someone were to come ask me, how should they build a pedestrian detector, I would advocate this approach, because I think it does work the best right now. So you assemble a whole bunch of images of people, call them your positive set. Assemble a whole bunch of images of non-people, call them your negative set. And now from these images, extract some, just to make it simple, fixed dimensional feature vector. And so rather than directly processing pixel values, we maybe want to process a slightly more invariant feature like edges. But once we, let's say, take an image, compute edges, and maybe this is, let's say, a 40 by 20 pixel image, and maybe we can compute a binary map that's 40 by 20 pixels. We can rearrange that map into 40 times 20 numbers. That would be 800. And we can think of these as feature vectors that we have in our training data set. And some of these feature vectors have positive labels, and some of them have negative labels. And now we can just give this to any learning algorithm. And perhaps if you open up your pattern recognition textbook, one of the first learning algorithms you'll see is a linear classifier. And so what a linear classifier does is it takes your input, your feature vector. So in our case, it would be this reshaped set of edge features, these 800 numbers from a 40 by 20 image. And given a bunch of examples of these with positive, negative labels, we would learn a linear classifier, which really is just a bunch of weights such that when we take the inner product with the feature vector, we tend to see a positive value whenever this came from the positive set and a negative value when it came from the negative set. And in our lab, we tend to use a particular linear classifier called a support vector machine. But what's nice about a linear classifier is you can look at it and kind of get an intuitive sense of what it's doing. And this is actually a linear classifier you would learn on edge features extracted from a large set of images of people and backgrounds. So what this thing is trying to do is you can imagine that this is going to respond well to an image that also has edges and edges at the same place that this thing has edges, the same place that this thing has high values. So this thing is going to respond well to an image where there's lots of vertical edges along the side of a person. So just to make sure we're also on the same page, an edge really is just a difference of pixel intensities. So at the side of a person's leg, you expect a difference of intensities from their leg to the background. And then around the head of the person, you see lots of diagonal edges. They kind of encompass the circular shape you see up here. Everyone's on board with me here. Okay. If you play in the vision world, you'll have seen these visualizations a lot. And now the way to actually use this to find people and images is you would now sweep this template across different image regions and keep computing this score. Whenever it was positive, you would say, yes, there's a person there. And hopefully when you sweep it over this region, you would find a positive score here and low scores everywhere else. And that's not an unreasonable way of building a person detector. All right, so any thoughts on how you might do this? So it seems like this person detector is tuned for people of particular sizes. In particular, if this was a 40 by 20 pixel image, it seems like it's only going to find people that are 40 pixels tall. So how can we use this to find people of different sizes? Any thoughts? You can speak.
Can we just make it vectors or scale it arbitrarily or whatever?
Yeah. So that's you can imagine kind of resizing stuff. And you could even resize your training images, but what's really simple is you keep this thing the same, and you resize your test image, and you just keep sweeping it over. So this is really the final pipeline. You sweep your template over, and because this template, the way you're scoring is with an inner product, you can literally think about this as a linear filter. And there's also, I think, a nice signal processing view of this, where this is going to respond well to image regions that look like it. So you can think about this as a matched filter if you come from the sort of the ECE background. Okay. Now let's move to, I guess, in some sense, the million-dollar question, which is, okay, but if you look at this filter, you can kind of tell it's going to respond to people that are standing, and seemingly this would not fire on any of you in this room, because none of you are standing. Okay. So how can we deal with the variations that we expect people to be in, that people are not all standing? People can look different, not just because of their pose, but probably because of clothing. If you look around the room, that's probably the biggest high order bit that makes us all look different. And also a whole bunch of other factors. If we're in shadow, if you take a picture of me outside with bright sunlight, that also is another reason why pixels look different. So there's all these variations in appearance. And really the classic struggle in vision for the recognition side of things is how do we build stuff that works across all these variations? How do we build one person model that can work across these scenarios? And A really simple approach for dealing with these variations is you think about these as subcategories, and you train a separate template for each of these subcategories. So if you had a big collection of images of people, you divide that collection into the images of people standing, the images of people sitting on a horse, and the images of people walking. And you just apply the same learning machinery to each group. Now, this sounds like a naively sort of simplistic way to deal with this variation, but it's surprising how effective this is. So I remember in my grad school years, I worked on, let's say, more traditional model-based approaches to recognizing people. And these kinds of models came around, I think, in 2005, and I was really annoyed at how well they worked, and they worked frustratingly well, this very simple approach. Let's try to push this to the extreme. So if it's the case that we can deal with appearance variation by cutting up our set of training images into little groups, what happens is we make the groups smaller and smaller. And in the extreme case, every image becomes its own group. And we just that seems like that's the maximum amount of appearance variation we can capture, given some finite training set. So if you do that, and I'll show an example of actual models you can train on images of cars, you end up with these kinds of templates, where you do see some kind of structure. It seems like this is tuned to find sort of wheel-like things down here, and maybe it's looking for some edges that look like the open door over there. But you also see that the template gets confused in that here's an image of a car behind a tree, and you can very clearly see that it's also, this template is going to look for trees. Because if all of this template has seen is this one training data example, it doesn't really know if the tree is part of the car or just something different. Right. Now here's a very simple way of trying to clean this up, which is you can take these templates, and then amongst your training set of cars, you can find the 50 highest scoring other positive examples that score high when you run this template on them. And you can take those templates and average them in. Right? So if you do that, what you end up with are these are what the new average templates look like. All right, so you can see now what happens is when you take this template and you look for other cars that respond well to this, what you happen to see is not all those other cars will have the tree in front of them. And so when you average all of those 50 closest matches, you blur out the tree, but you keep emphasizing all these other wheels and all the good stuff. So this is why in this subcategory view of the world, you don't want to go all the way down to one single training example, and that you get some nice properties of averaging by having groups of examples in each subcategory.
So what's happening in the lower part is you're just taking average of the weights over the top 20 responses to your filter, right?
Yeah.
So one question that comes to mind immediately is that it is sort of averaging. You're assigning equal weight to each template, to each pattern that you have, and then you're averaging that. Wouldn't it be more appropriate to look for another distribution over this data?
Weighted average, yeah. So in fact, instead of just averaging, what instead you can do is take those 50 examples and treat them as your category and just run it through your learning algorithm. So that won't just take a naive average. It'll do some sort of smart combination of stuff. But intuitively, if you look at what's learned, if you do this in practice, the high order bit is that it looks like an average. But you're right, you can get a little bit better by taking, let's say, a weighted average where you weight certain things more. But you let the learning machinery deal with that. Okay. All right, so the high order bit is that, okay, this is why you don't want to go down to a single training example. And so in practice, you want to find some happy medium. If you take your training set and you split up into groups that aren't too small, and you train an example per group. So why doesn't this sort of solve the $1 million vision question? Why can't we use this as a technique for handling the appearance variation that we see? And I think the reason why is this sort of curve, is if I actually try to collect training images of people, what I'm showing here are different subcategories along the x-axis, and I visualized some examples here. And these are subcategories organized, let's say, by the pose of a person. And on the y-axis, I'm showing the number of training images I can see in any sort of realistic training set. So what this is saying is that it's really easy to collect images of people standing. And also, it's really easy to collect images of people sitting. An example of that is just look in this room. Those are the two poses almost everyone is in. And as we move on to more other things, such as interacting with objects, machines, animals, performing yoga, all those examples, it's much harder to get examples of that particular pose. And so I think oftentimes this kind of plot, this distribution plot, this is where the name of the title of the talk comes. I would call this a long tail curve. where there's a lot of probability mass in the tail. So what that means is you might think that if you see a rare pose, if we consider a rare pose, one reaction is that, all right, well, if it's rare, why do I even need to model it? Because I might not even see it at test time. And that's actually almost a reasonable response, except that there's a whole bunch of these rare things, and the collective set occupies a non-trivial fraction of the overall probability mass. And so you can't just ignore it. And personally, I think that's where the recognition is at right now in vision, that we're getting the head right. All the dominant iconic viewpoints and iconic appearances of objects, we can build models for them, for nice profile views of cars, for pedestrian views of people. But all this rare stuff, that's kind of where the remaining challenge lies. Okay. And just to be a little bit more concrete about stuff, is that to verify if you have a distribution plot, to actually see, is it really a long tail curve, the math is actually quite simple. You can assume that the counts are equal to the index raised to some value. And so if you hit this equation with a log, you can see that you should see a linear relationship. So this is one way to verify that these kinds of distributions are in fact follow a power law.
I have a question about the sample data in the tail. Do we need these samples to be a real image or just synthesizing?
So right now, I'm thinking about doing this on real training data. But in fact, one of the approaches, the solutions for dealing with this, you've hit the nail on the head, is if you have access to synthetic training data, all of a sudden you're not limited by these distributions anymore, because you control, you can generate more images in the tail. So that's one, I think, solution of dealing with this. But as a point of fact, right now, we don't really train models with synthetic training data. We train models with real images. As in, it's not quite clear if we can go to that route yet, although I personally think that's a super exciting direction to explore.
So by using a power law, does that mean that your observation in real data is that you see tails that are longer than you would expect from a normal distribution?
Yes, yeah, exactly. And so this is not just true of people, but any object category. This is sort of an interesting phenomenon that if you take any, if you actually compute statistics on real images, you see these long tail power law distributions everywhere. So if you try to understand the various appearances of cars, and so here you might think, well, cars are more rigid. There's not as much variation as people. But you can still open doors and close them, and you can have clutter in there or animals in the front seat, and you can have specular reflections. And each of these generates kind of a unique appearance that ideally you would train a template just tuned for this, but because it's so unique, it's going to be hard to get lots of training data. So the same argument still applies, that we can build good models for detecting cars and these sorts of viewpoints and reflection conditions, but it's hard to build models here. Okay.
It seems like there's an issue beyond just having enough data to train on the long tail. It's that you end up with a bunch of templates, and the detection then scales linearly in the number of templates.
Yes, so great point. There's also a computational issue that I'm shoving underneath the rug. So we'll talk about ways to try to reduce that. But I guess the perspective that I'm trying to argue is that even if we ignore the computational issues, even if we had all the computation in the world, there's this fundamental restriction that the data, I think, limits our success because of these rare examples. Even if you threw crazy horsepower at it. And kind of envision now, we are throwing crazy horsepower at stuff. Okay. Okay, so at some level, this is also, like I said before, not a radical observation. We know this, that if we compute statistics on stuff, on real natural images, we tend to see these long tail curves. So if you go and you just count the number of objects you see in your daily life, you see a long tail distribution. You see some things a lot, and same thing in this room. You look around, you see lots of people, you don't see lots of cows. It's the world we live in follows these kinds of distributions. So I argue that it's not like a bias of a data set, it's a property of the visual world. But one thing that I think but the reason why I'm kind of belaboring this point is that I think it's kind of striking that in vision, we become a very empirical field, and a lot of progress has been driven by data sets. And virtually every data set that has been collected has worked very hard to minimize this long tail. So we work really hard to collect balanced data sets. When we collect object categories throughout sort of our history, we'll work really hard to collect more and more examples of those rare categories. And in my view, this is just putting a Band-Aid on a much deeper problem, in that these long tail appearances still occur at the subcategory level. All those nuisance factors that we're trying to address in vision, we still have to figure out how to address. And so I think we should be kind of embracing this rather than running away from it. And so just as one more point about this fact, I'm involved with a whole bunch of other collaborators on what we hope will be sort of a next generation vision data set, Microsoft COCO. And it's sort of being funded by Microsoft. That's why they get to put their name in the title. And most of the time, effort, I shouldn't say most, but a significant amount of the time, money, and effort we spent on collecting the data set was in filling up the tail. And I try to sort of humbly argue off to the side, maybe we shouldn't be doing this, but nonetheless, we sort of felt like, oh, we needed to do this in order to make this useful to the community. So I'm hoping that maybe in the future years we won't do this, so we'll let the kind of data speak for itself. So that's, so yeah, in my mind, this long tail isn't just a reason why vision is hard. I kind of think it's the reason why vision is hard. Because there'll be some variations that we won't see a bunch of examples of, and that means that data-driven approaches will be kind of limited. All right, so hopefully if I've convinced you.
Sorry, this power law distribution arises in many other things that you were saying. Like also language is also one of them, for example?
Yeah, definitely.
Word occurrence and stuff like that. So would you go far enough to say that this is the reason why machine learning is hard?
Yeah, I think so. This is essentially an argument about like generalization, that in some sense I think generalization, in my view, is sort of the key problem in machine learning, is how do you deal with stuff that doesn't look like what you've seen before. And at some level, the reason why it's kind of a little confusing is that you might think in the world of big data, why should we care about small data problems? Why should we care about how do we solve things when we have little data? And I think the answer is because of long tails. That's why we care about little data problems. Because even in the world of big data, we haven't eliminated the small data problem. So in language, so I think Chomsky used the phrase the poverty of the stimulus. I think it's the same kind of argument, that we're always encountering new sentences, phrases, paragraphs that essentially we've never been seen before. So how do we deal with how do we construct models that deal with that? Okay, so the first kind of line of attack is going to be what someone already suggested, and this idea of synthesizing data. And in fact, I think this is already happening underneath the hood for a lot of these learning systems that are data-driven. And instead of calling data synthesis, what's usually used is a term called data augmentation. So even if you're going to build a machine learning model for recognizing digits, you take your training set of digits, and what you do is you add perturbations to that by rotating your digits a bit, by stretching, by applying transformations. So I think of this as you're synthesizing variations that explore the tail. You're synthesizing variations that you didn't naturally see in the data, because if you did, you wouldn't need to do this. And so a kind of an interesting phenomenon is that usually this is dealt with as, it feels like this is dealt with as a cheating approach. And that if you go to these recognition benchmarks and people evaluate themselves, there's actually a different leaderboard if you use the original data set versus if you use the augmented data set. Somehow you're penalized if you use the augmented data set. And one of the things I want to convince you is that we shouldn't be thinking that way. And I'll try to give you a crisp answer for why in just a second. So there still is this resistance to, well, somehow this is a dirty thing to do, but I think people in practice know this is an important thing to do. So if we push this idea to the extreme of augmenting data, if we have a synthesis engine that can generate, brand new scenes at will, then this gives us a way to generate as much data as we want, and we can clearly explore any tail that we would like to, because we have complete control of what's being synthesized. And so I actually think this is an interesting perspective to try to reconcile this with these data-hungry learning architectures that everyone is using in vision now. Hooking that up to a computer graphic synthesis engine, because it just seems like a very natural marriage. This needs data, and this can provide as much as we want. But right now, at least in our group, we don't have the expertise to do that, so we're trying to explore something in the middle here. And this is what I would call image-based rendering, where what's up here is an actual real image, and I just went in Photoshop and cut this up into layers, and then moved the layers around, and I can generate what looks like a sort of reasonable approximation to a new pose. So this is like a poor man's renderer. And so maybe we can use this as a form of aggressive data augmentation. It's not just rotating an image, but it's sort of going in, putting in a little bit of smarts, in this case, reasoning about depth and layers to generate a new image that's varied. And maybe, for example, I could explicitly use this to generate poses that would otherwise be hard to see. Yes?
Wouldn't natural extension to this be considering video data and finding particular locations where you can identify them and then see the change in geometry?
Sure. So actually, I'll show you an example for video analysis right now. So maybe this is exactly what you're saying. So let's consider the problem of tracking a person in a video sequence. And just to make life a little bit simpler, I'm going to assume sort of an old style assumption, which is the first frame is labeled. So I have an initialization for a tracker. So I'm told the articulated pose of this person. And my goal is, in all the other frames, run an automated algorithm that will predict how this person is moving around in an articulated fashion. And so what we're going to do is exactly what I did for that Obama image. We can take that first image, assume that I can decompose it into layers, or maybe that's even labeled for me. And when someone has labeled this pose, they've labeled this arm is in front of this torso. And once I do that, it's fairly simple compositing to move these layers around, re-render them, and generate a new image of the same character and maybe other objects in different poses. Right? This is just what I showed before, essentially, with the Obama image. And now what I can do is, if I have that first image that's labeled, and I have a library of poses that someone has given me, and so these poses can include as many of the rare, weird tail ones as I want, because it's just a library of poses, I can now generate images for each of these new poses using the pixel data from here. Right? And I can now use this as a training set for a learning algorithm that can now try to predict out what the pose is. So maybe I can treat this as a regression problem. And I can give this to any learning algorithm you would like. So the latest phase is let's say, a deep learning architecture. We could give it to that. But one thing that it turns out is interesting is that it seems like these images are so accurate that what I'll do is I'll just use the learning algorithm that I'll use will just be nearest neighbor matching. So given a brand new image, I'll just match it to one of these images. And furthermore, I'll just match based on pixel intensities. I won't even use any fancy edge or transformation. The one little trick is it turns out that it's helpful to use a color space that makes sense, like LAB as opposed to RGB. But it's still matching pixel by pixel, just computing square distance. And the second trick to make this to work is because the renderings that I generate are kind of crappy, I'm just going to shrink the image and make it smaller and then match small images to each other. And so I can kind of show you this thing working. And so at top is the test video. At the bottom is the best matching synthesized frame. And this is the actual features that are being used to match. It's just a blurred, low-resolution version of that frame. Okay, so you can see that the rendering is not great. It looks kind of awful, actually. But in the blurred sense, it works pretty well. Okay, so here's a case where now we would put all our smarts into synthesizing the training data, augmenting the training set. Now the learning architecture is kind of trivial. And so I don't know where this fits in that scheme of cheating or not cheating. Even though this is kind of quite simple, there's a couple of interesting things that this can do that's normally hard to do. So one is, I think one of the challenges in understanding articulated pose is self-occlusions. So when the arm is outside here, it's a little bit easier to analyze and predict what's going to happen. When the arm is in front of the body, you sometimes see strange edges depending upon if I'm wearing a t-shirt and you see skin or if I'm wearing the same colored arm sleeve as the torso. And kind of managing that is a difficult, complex appearance interaction. But that just falls out naturally from these rendered images because I'm just rendering the right shirt or the right arm on top of the right torso. I'm rendering the right edges and the right appearances you expect to see. I think another kind of interesting aspect of thinking about synthesis in video is that we don't have to synthesize appearance variations. I don't need to synthesize all possible clothing combinations, which I would really need to do if I want to build a training set for building a true person detector. What I really want is a Phoebe detector. And so I just need to really synthesize variations with the same piece of clothing. So I think somehow synthesis sort of works well in this setting because we only have to worry about scene-specific appearance. Okay, and you can compare it against some methods, and what's kind of fun is there are some state-of-the-art methods where this actually beats. This is on par with some much more sophisticated techniques, and this really comes from just this, design of a custom training set that which is fairly simple, I guess, to actually design that set. So I'll talk about one more example of this idea of synthesis as a way of reconciling the tail, of exploring these rare poses.
So this is clearly using the fact that the shot is from a static camera.
Yeah, so you're right. So well, actually, the camera's moving a little bit, but then what I would hope the answer would be is that you synthesize translations as well. So as you have these different layers, you move things around. And of course, the more things I can just say, oh, we just throw that in the extra set of parameters you have to synthesize. And in practice, things can get hairy because you might have to synthesize a large set of things. And so computation is an issue with the approach that I'm talking about here. And I'm putting that underneath the rug. But at some level, you could take that data set and then once it's synthesized, give it to some other off-the-shelf learning algorithm, and it'll figure out how to do things quickly. Just in the interest of time, I'm going to keep going until I hit the next stop point for questions. I just want to show you this one other synthesis approach, which I think is fun. And that is thinking about wearable camera data. So this is something that another task that our group has been interested in that if you have wearable cameras that are mounted on, let's say, a Google Glass iframe or mounted on a GoPro, looking at the kinds of data that you see and trying to analyze this. And something that I think I'm surprised not more people are doing, but to me feels very natural, is instead of just sticking an RGB camera on a person, stick a little depth camera on a person. And now as they go around and do stuff, you collect depth images of what they're doing. And one thing that's kind of neat is that these depth cameras have a small baseline, meaning that the accuracy of depth that they extract only really works up to what I call sort of a reachable workspace. It's not, let's say, more than a meter. And that's also exactly the space over which you can kind of touch stuff. So it's this neat regime that so we use this term near field. So you get 3D data, or rather, I guess, 2.5D data for the near field, and anything else beyond that, it blanks out at white. And furthermore, humans arguably use this as well because this is also exactly the regime over which our stereo works. So this is one place, this is sort of a tongue-in-cheek comment, but where you can extract depth and it's not cheating. This is what people do too. So this is a natural place to now try to use this for analysis of these near-field wearable scenes. And the reason why I'm putting this into the story of data synthesis for the long tail is that a significant advantage of depth is that it's much easier to synthesize training data. And the kind of well-known example of this is the Microsoft Kinect pose estimation system that does exactly this. So I'm sure everyone knows about it by now. But they use synthetic data of 3D models of people, and then now, given that, you can contort them into any kind of pose, and you can explicitly contort them into lots of poses that might be hard to otherwise naturally observe, and then feed this to a learning algorithm, and there you go. So we just follow this exact same approach for these wearable scenes, where we have a virtual 3D character, we put a virtual camera on his torso, and we generate scenes of what you could do, what this virtual character would do. And here we needed to use a bit of domain knowledge of how do people normally interact with stuff. And it turns out there's lots of relevant work from the robotics literature on sort of types of graphs that normally are used. And we can use that to design this synthetic training set. And so once we have it, the way that we're going to analyze these scenes is, you guess it again, is just by naive matching, just like the previous approach. Given a new image, I'll match it to some stored 3D synthesized exemplar. And that's how, let's say, I will produce these kinds of interpretations of how I think the arm is behaving and how I think the person is grasping different objects. Okay. And the place where, so in some sense, this is just an application of the Kinect insight to a slightly different, I guess, domain of wearable footage. But what I think is really interesting is I had a student do a pretty big evaluation of a whole bunch of techniques for solving this problem. And so this is a piece of work that will appear in ICCV, and this includes as a co-author Jamie Schotten, who's one of the designers of Kinect. So we got his blessing to do this. So what we do is we compare a bunch of Connect-style approaches that are random forest decision trees, and these are the two red and orange lines. And we compare it with just simple nearest neighbor matching using different training sets. And so this is nearest neighbors on the same training set that was used to train these random forest classifiers. And this blue curve up here is actually a deep model that does quite well. But what we were kind of surprised to see is that nearest neighbors does about as well or better than almost all existing systems we could find for this task. And what that suggested is that most systems actually couldn't generalize beyond the training set. And they couldn't even do that particularly well, except the only little glimmer of hope was these deep learning systems. And so I'll talk more about that in just a second. But here's another example where just simple matching to what's stored in the training data, when the training data can be enriched through synthesis, actually works pretty well. And again, this is expensive. So I'm shoving that under the rug.
Can you just tell us a bit about the synthesis? You have hands. You're putting them in all sorts of random configurations?
Yes.
Okay, so you'll have really bizarre.
Yeah. So, and that's something else I'm showing in the rug is, okay, so we try to get some domain knowledge about like good prototypical grasps for hands. And that's something that I think is still the Achilles heel of the approach that I'm suggesting here. Is that if you're actually going to synthesize, you need good synthetic models. You need to know how people do stuff. And that's not an easy thing to do. We were able to get away with stuff here by just kind of hacking stuff together. But we definitely found that to be the difficult thing. But philosophically, the point that I wanted to summarize with these two approaches on using videos for scene-specific synthesis and then synthesizing depth maps was that usually, if you have these engines that generate training data, and now we feed this training data to a learning algorithm, typically envision we fight over territory here about who has a better learning algorithm. And it almost seems like what I'm advocating is that maybe we should be fighting over territory here, which is we sort of show our smarts in this generative synthetic side. That's where we put our domain knowledge. That's where we flex our muscles as vision researchers. And once we generate the data, well then, okay, then we can use something else to quickly search or index it. So I just think this is another perspective on the problem. Somehow we want to be algorithm designers and we're ashamed to be data wranglers, but maybe we should be designing algorithms for generating better data. Okay. All right, so that's a little philosophical point. But I will totally concede that building good generative models is hard. And so that will lead us through to this third section. Okay, so I'll pause for questions. Yes?
So making a philosophical one, I'll also try to make a
Please.
So when I was listening to the long tail problem, it seems to me that maybe one of the biggest issues is because we're dealing with a very high dimension. Because as you know, when you're in high dimension, every point becomes like an outlier. And so in a way, synthesis is one way, but in fact, when you're talking about shapes, I think you're already approaching the problem by dealing with the dimensionality. So maybe the way is to how to compress, how to reduce the dimensionality so that you get to a much lower dimensional problem. And so I was wondering whether you would be dealing with the long tail and try to compress or reduce the dimensionality of the long tail of example and then integrate that into your original problem. So I was just curious whether this dimensionality is an issue that is important.
Sure. So I think what you're hinting at is that, okay, well, if you think about these as like points in very high dimension, there's got to be structure. They're not just arbitrary. Maybe if you could, I don't know, if they live on a manifold, if you could understand the manifold, then that would be another approach to dealing with this. So what I'll talk about here is a little bit more of an algorithmic approach of dealing with these samples for which we have little data. So it's not quite an explicit compression, but I think it has that intuition that you're talking about. The other thing that I'll note is that, okay, well, why don't I sort of dig into this and maybe we'll revisit that point that you raised. Okay, so recall our original motivation for synthesis. And I said sort of the thing that I'm still brushing over is we need to be able to generate good generative models for synthesizing training data. So instead of trying to explicitly generate extra data, let's try to give this skewed distribution to an actual training algorithm. Let's have the algorithm try to figure out how to resolve, how to deal with this hard bit, the tail. And argue one approach for dealing with that is if this algorithm or if this learner can learn some knowledge from the head, for which it has lots of data, and then apply that knowledge to the tail, for which it has little data. And one way of doing that is what I'll call compositional representations. And so in vision, probably the more common term is parts. And so this is a way of thinking about visual appearance that has really been around for 50 years in vision. And sometimes it's called pictorial structures or constellation models. And the basic idea is instead of building a visual template for the whole object, you build a template for little local regions of the object or parts. So maybe you build a little visual template for the head and a visual template for the arm or elbow. And now by moving these templates around, you can almost on the fly create subcategory templates for this pose and for this pose. Okay. And so Jim hinted at that probably the work that I'm most well known for is a particular instance of these part models called deformable part models. And I'll just give a little, I wanted to talk a little bit about that in the next few slides, but in the context of this synthesis perspective that this agenda I've been trying to lay out on you guys. So even if you've seen DPMs, you probably might not have seen them quite like the way I'm going to talk about it. But just as a point of fact, I prefer thinking of them in the way that I'll talk about it now. So let's dig in a little bit. So I'll show some math, the few math slides in this talk, for exactly how do these representations work. And the way we're going to think about this is in terms of a scoring function, just like we had a scoring function for a linear classifier. Here I'm going to think of X as an image, and I'm going to think of Z as a collection of XY pairs, XI, YI, which are just pixel positions of different parts. So imagine I have a model here that has 12 parts. So I varies from 1 to 12. And what I'm trying to really do here is given an image and a collection of hypothetical part locations, I want to generate a score. And the way I generate the score is I sum over each part. I go to the image at that pixel location. So maybe I'm hypothesizing that the head is in the top left corner. So I go to the top left corner of the image, grab some appearance descriptor. I'm going to call that phi. And then just take the dot product of that with a template tuned for the head. And I get sort of a local head score. And I sum this over the head, the leg, all the other parts of my model. And now I get an overall score associated with this image and this hypothetical placement of parts. Okay? So you can think of this as sort of the natural extension of a linear classifier tuned for each individual body part. And now, although it seems simple enough, you can simply, for any hypothetical location of parts, you can show with some fairly simple math that the score you get for this image and that location of parts can be replicated by just generating one global template that's synthesized by moving these templates, these WIs, to those ZI locations. Right? And this works out because everything is linear. There's nothing super complicated going on here. But now, so if I evaluate this model for one particular set of part locations, I get a particular WZ. It looks like this. And if you give me another Z vector of XY locations, I get another W of Z. It looks like that. And I can think now about defining a family of these templates. And now the way that I'm going to do recognition for a person is, in the old days, the way I would just compute a score of just some image region X with an inner product of weights. And if that's bigger than 0, I would say, yes, there's a person here. And now I'm going to search over all the global templates that I can construct by indexing part locations in some set of candidate part configurations. And I'll just take the maximum score amongst this set, which is nothing more than saying the maximum score of this set of global templates. And if that maximum score is above 0, I say, yes, there's a person there. And a little extra sugar on top is that you can look at the Z star, you can look at the example template, the particular template that triggered the high scoring detection, and that can show you where the parts are. Right? So this way of recognition, you get an extra bit of information associated with the detection, which is what were the Z's that triggered that.
How is it different from actually solving the highest score location and getting the solution out of it?
This is the same thing. So except what I'm saying is that, so if you're familiar with DPMs, there's like fancy ways of doing this search. And I'm saying instead, you cannot do anything fancy. You can literally construct every combination of parts that corresponds to some template. You can literally construct all those templates and just take the maximum score across this template, and that gives you numerically the exact same score you would have gotten with the original procedure. I'll dig more about that in a second, but the reason why I like this is that I claim that this is the model, this set of global templates. That's the way this model believes the appearance of people can be characterized. And the other stuff is about how to do efficient computations with that model, which is important, but this is what it's claiming about the appearance of people.
Is this factoring in occlusion?
No. So if we wanted to, we could try. In that, actually, no, I should say this, because this vector, each of these z's is a vector of xy locations. So I could imagine that in this set, I know that if I put the arm here and the leg here, I should turn the torso off because I can't see it. So that can actually, I'll take that back. So actually, occlusions can be modeled here. And that's because there's really nothing smart. It's just indexing into a set of part locations. And it could be that in that set, you turn off certain parts. Okay. And so now to kind of hint at the other point, that rather than actually computing the maximum over this set of global templates, you can be a bit smarter in saying that, okay, well, if the way I constructed these global templates was they're all just combinations of parts and heads and elbows and torsos at different locations, then what I can do is take my head, torso, and elbow parts, first score these densely at all image locations, and you can do that with a convolution. I can cache these scores, and now on the fly, I can compute the score of any one of my global templates with a bunch of lookup operations. Okay. So there's definitely ways of making this fast and efficient. And in practice, you can make this so that the lookup operation is quite fast, and this initial convolution is the bottleneck. So at the end of the day, you can make this quite kind of zing in terms of speed. But the real question I want to address is, how do I get the set of part locations? This kind of goes to your question of, depending upon how complex that set is, maybe some parts are not visible in some configurations. Who tells me all this set omega? And one thing I could do is just, if I was given training images with part locations, I can just use these locations to define the set. So if in a certain training image the arm was occluded and it wasn't labeled, then I just wouldn't place that arm part down anywhere here in this image. So this actually could handle occlusion in that sense. Okay. All right, so now what this allows us to do, it almost allows us to build a subcategory template for every training image. But now we have the example, we have the added benefit of we're using lots of images to train the head part and the elbow part. So it's kind of the best of both worlds. It's very flexible, but it has a lot of that sharing that we talked about from the very beginning. So in some sense, this is a sort of simple architecture for doing this knowledge transfer, of taking information. So we can use images of people standing, which we have lots of. We can learn good head models, elbow models, and knee models. And by rearranging them, we now can learn good models for people in these kinds of poses. So it's a simple architecture for sort of dealing with this, for examples for at least which you've seen once. Okay. Now, the last sort of, I should keep an eye on the time here. Okay, if you guys want to hang around. The last kind of hurdle with this is that if you really buy this long tail, and hopefully I've convinced you a little of this, is that what's even scarier than the examples that you see once are the examples that you never see, which there exists even more of those. And the approach that I just talked about seems like it doesn't give us a way to attack that stuff, because this still requires us to have seen at least one configuration of those parts for me to instantiate a global template for that pose. But there's poses out here that aren't even in my training set, so how do I deal with that? So I'm going to call that the zero-shot learning problem. And the way we deal with that is really alluding more to this philosophical point that we talked earlier, which is synthesis. So given these poses that I have seen and these marked up set of part locations, assume I have some synthesis engine that instead of synthesizing pixels, it synthesizes new locations of parts. And if I can have this guy, then I simply just plop down parts at those locations, and now I can build templates for things that I've never seen before. Okay. And so then I can think of the final model as just having a large set of omega, where it's the original set of poses that I've seen, plus some new stuff that was generated from something yet to be specified. But I can almost imagine this as a synthesis engine, but a shape synthesis engine. And so now this is the new model. Okay. And so where do we get that shape synthesis engine? This is where I would appeal back to the same intuition we sort of hinted at before. So for some things in computer graphics, maybe we do have good shape synthesis models. So I'm showing here a very simple Gaussian model of landmarks on faces. So I'm showing both the mean face and modes of deformation away from that mean. So these are eigenvectors. It's a way of visualizing a Gaussian fit to a collection of landmarks. And now that I have a new collection, a parametric family of landmark locations, I can just plop down parts at each of those locations. Now I have a near continuous family of subcategory templates. And what's important is that most of these were never seen in training data. Okay, so most of it was synthesized. Okay. All right, so this general, so for those of you who have seen DPMs before, this is how I prefer to think about deformable part models. It's a way of constructing a set of global templates, a small fraction of which you've seen, and most of them you haven't seen. And that generalization comes from some spatial model about how we can generate new locations of parts. All right, so this general technique we've used to try to solve a bunch of problems, including estimating poses of people. This is what Jim was hinting at. Something else that I think is kind of neat is if you now use a synthesis engine that's a literal 3D model, a 3D CAD model, what this will do is generate a family of 2D templates, each of which is associated with a particular CAD shape and viewpoint. And now we can just do recognition by searching through this collection of templates. But now anytime one of these templates fires, there's a 3D model and viewpoint associated with it. And so it's not like sort of you do 2D detection and then you fit some 3D model after the fact. You can't help but have a 3D model associated with every detection, because that model is used to define where these parts should be. Okay. And here's also an example of applying this on faces. So a face model that works pretty well. So in some sense, this is sort of the main message I sort of wanted to get across. So kind of the big challenge I think in vision is handling this. Even in the world of big data, we still have to deal with small data problems, those variations that we don't see a lot of. And one approach for doing that, if we can synthesize data, then we have explicit control of adding more data in that set. But another approach, too, is that you can try to think of algorithmic solutions for dealing with that. And one is if we can share or transfer knowledge from the dominant cases to these rare cases. But that itself, it seems like it'll handle, let's say, the one-shot learning problem, but not the zero-shot learning problem. How do we deal with stuff we haven't seen? And so synthesis seems like an architecture for doing that. I have more slides, but I feel like you guys are tired.
No, please, more.
Okay, so just maybe a 2-minute taster of where some sort of forward-looking directions. So one challenge about the story that I laid out with parts is that I described an approach where you kind of needed to know what the parts were. And so what are the right units for sharing in synthesis? And so for a long time, if someone asked me, well, what are the right parts for a person? I would say the answer is obvious. It's kind of the skeletal limbs. And what I think has been interesting in recent history, the community has challenged this. So there was an argument made by the Berkeley Vision Group that, well, this notion of part, it's too weak because it's just two parallel lines. And if you build detectors tuned for them, they'll fire on everything. Instead, you should have slightly a bigger notion of parts. It should look for maybe a piece of the arm and a piece of the shoulder. And now, by building a detector tuned for this more generalized part, they called it a poselet, it'll have much higher accuracy and sort of result in, it's a more natural unit for sharing and synthesis. And in our group, we actually had the complete opposite intuition, which was the reason why these things don't work is that limbs aren't really rectangles. And so instead, we should cut these up into even smaller parts. And by letting the small parts move around, we can model different widths and different subtle shapes of limbs. So essentially then, I think of this as a question of representation. So what are these units? And the way that we tended to answer these was through introspection. We just think about it. We know this is a better representation or part to use. And this took on the time scale of years. And so this is the kind of thing that a computer should do for us. And the way that we answer this question, which one is better, is we saw which one worked the best. So this really should be something that should be automated. And so the kind of work that we did, that Jim was hinting at for deformable part models, was trying to automate this procedure. Where assume that your training data that you're given, you're not actually told where parts are. You're just given positive examples and negative examples. And we try to come up with a latent guess of where we think parts should be. And the way we evaluate the goodness of that guess is, given a hypothetical set of part locations, we can then define a family of global templates. And then given this family of global templates, we can evaluate the accuracy of those on this original positive and negative set. And so that gives us a way to compare one hypothetical set of parts with another. And then we just do a search across that space, which is a hard search, but at least we kind of formalize it as trying to optimize something. Okay. So the other challenge that I didn't talk about is what happens if the part that we're trying to learn, if that we suffer from the same long tail problem. Maybe there's a particular arrangement of my elbow next to my torso that I won't see a lot of. And so it feels like I'm stuck. How do I deal with building a good template for this? And the solution here, I think, is we'll apply the same solution we had before recursively. Decompose your part into subparts. And very naturally, what you end up with is a latent hierarchical model. And this is the way that I'd like to think about deep models. It's a way of discovering structures of parts and subparts and doing it in this hierarchical fashion. And so we have some work about trying to reconcile this view of sharing and synthesis with the deep world in which vision is obsessed with these days. And so I really won't have time to get into stuff, but in some sense, if this is what deep models are doing, I actually believe in that story. Because to me, it's sort of motivated by this notion of these long tail things. You see lots of things, you see some things a lot, and you see a bunch of things, a few, you see a bunch of things rarely, and modeling that stuff is hard, and we can do that by coming up with compositional representations, decomposing something big into little bits that can be recomposed. But we ultimately, even the little bits might be hard to model, so we want to do that recursively. So that story makes sense to me. Of course, one of the difficulties with deep models, we don't really know what's going on inside. So we're trying to peer inside with this view as the agenda. But maybe then I'll sort of end with that. So this is how I think deep models fit into this perspective. Okay, thanks.
We have time for as many questions as Deva was willing to take.
Yes.
So one of the properties is that children have, as I say, one of the properties that you got trained on many more images than, for example, children have ever seen. And one of the things that children have as a property, they can see one example of an image and then generalize it and capture them in lots of other things. Does your model let you do something like that?
Yeah, so I think that this notion of transfer should allow you to do that. Because what happens is that is what one-shot learning is. You see one example, yet you're still able to build a good model of it. And so this is happening from this repurposing from this compositional model. The basic, there's always some kind of hidden underlying assumption that's happening here. So how can you come up with a good model for something you've only seen once, or even come up with a model for something you've never seen at all? And the underlying assumption is that I can model things that I haven't seen as rearranged bits and pieces of things that I have seen. That's the underlying kind of compositional assumption here. And to me, that actually is kind of a reasonable, like that very much feels like a part analogy. And so if your data exhibits, if you believe that's a reasonable way to guess about things you haven't seen, then I think this sort of architecture makes sense.
synthesis of or adjustments of the templates look at to video? Since you have the actual models, big models.
I think that's a great idea. So personally, this is how I would approach. This is sort of this goes back to kind of some work I did in my graduate thesis. But this is how I'd like to think about video analysis. So the example I showed with tracking the friends data with that embarrassingly simple approach, just generating variations with that first frame. To me, what it suggests is if you could actually generate models tuned for the particular video setting, then all of a sudden analyzing the video becomes much easier. So then, to me, then the challenge would be when we address videos, or a nice way to think about video analysis is that we should be thinking about how do we tune our generic models to be specific for this video sequence. It's almost a learning problem, a little bit of an unsupervised learning problem. And so I'd like to approach video in that way. So I think that's a very cool direction.
So the interesting part about what you just said is this connection between the synthesis and the finding the parts at the same time. And it seems to me that videos, because temporal continuity matters so much. What you did when you generated Rachel's body moving around like that is you had a sequence of part identifications here. So something might be ambiguous in frame one. It starts to eventually evolve into something that makes sense. So I think there's some sense in what he was saying was that you develop that model and you carry it on through it. Because that's what a child is, as David was saying earlier, a child hasn't seen those images, but has seen things like that move many, 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 many times and interacted with them, picked them up. And that's why I really like your handwork too, because you can evolve that model over time.
Yeah, I very much like this. I totally agree. This notion of particularly the egocentric thing, the egocentric setting seems like it lends itself to this almost like online learning. Like it almost feels like this is how a kid should do it. You move around, you grab things, and you figure out stuff about the world. So you should be updating your model on the fly. Yeah. So I'd love to be able to kind of merge that a little bit more concretely with this this view of synthesis. I haven't thought enough about that, but it totally makes sense that video is a natural place for learning. Yeah.
Well, and the other part of it is, I guess what I wanted to hit at was that when you first tune something to it, you kind of establish a viewpoint on it.
Yeah.
You say, oh, I'm looking at Rachel sitting there and I'm in front of her, and there's a background, and that sets the context from the whole, for which everything derives.
Yeah. Yeah, no, I completely agree. Particularly, it seems like, so in settings where there's a stationary camera, it seems like it's such a huge win to have that context. That almost makes sense, like that's the first, either you should like have it in there or you should learn it, because it's like night and day if you have that versus not having it.
Right.
What are your thoughts on validation? So you've got a synthetic model, but what you're trying to validate that it's good for is on something that you don't have a lot of data for. I mean,
yeah, no, I completely.
It's like you did the model because you don't have data, but now it's going to be hard to validate the model.
I completely agree. So I actually think that this long tail view of the world, there's actually a double whammy. And one is it's hard to learn stuff because you don't have a lot of data for it. And secondly, even if you do a good job of learning it, it might not show up in the results because it might not even be there. So I think this is, in my mind, kind of a bigger issue with the way we evaluate things. Exactly, validation, where we tend to evaluate things based on average case analysis. Almost all benchmarks in vision work this way. And when you do average case analysis, you naturally care more about the dominant cases. If you just get that right, you'll probably do really well. And so, so I kind of believe we should be doing something else that forces us to look more at these difficult cases. So, for example, worst case analysis. This is what CS theory has a tradition of. And you could argue at some level, maybe even make sense for vision. It doesn't really matter on average how many times you fall off a cliff. It matters if you fall off a cliff. And we don't score things in that way, but maybe that would force us to care more about these corner cases.
In the car example that you showed there, you were synthesizing different models. I was wondering if you have any insight into how to search over those large number of models.
Yeah, so we didn't do anything fancy. There, we just synthesized all of them. And so the one little bit was I hinted at that if you generate all those 2D templates corresponding to each parameter of that 3D shape that you're exploring, as I said, rather than actually taking these 2D templates and evaluating all of them are still constructed from a common vocabulary of parts. So there is a noticeable savings you can get by first scoring the parts everywhere, caching those scores, and then doing some fancy lookup operations when you actually want to evaluate each of these global 2D templates. So that's just a way to speed up the 2D search over those templates. There's also this point of first even generating those 3D variations. That we just do with brute force. Does this distinction make sense? Yeah, so I don't have a quick way around that. There is a sense of once you start doing things hierarchically, which is what's happening, I think, in these models, there is a little bit of generative synthesis that's going on there. So here we don't explicitly, in this setting, we don't do explicit synthesis. We could, I guess, but instead we do the same kind of convolution that we did in the parts. And now when we search for part locations, typically in convolutional neural nets, you end up taking like maximum scoring part locations or maximum scoring filter locations over some window. That's a max pooling operation. And now we're sort of getting into the weeds of exactly how these deep models can be thought of as parts, which probably is best done offline. But there is a sense of, I think this tries to address a little bit of that, searching through the synthesis space in an efficient way as well. There's another question I saw. Go for it.
How sensitive is the synthesis approach to the skeleton you're using to do the synthesis? Because it kind of feels like there's kind of almost a nice opportunity. Say you're interested in a baseball player's pose, but then now you can think about where his bat is in space. But that's not part of your synthesis, obviously, because you haven't modeled that in your skeleton. Do you have any thoughts on that, or how you can kind of generalize from a basic skeleton?
So in the sort of view of things where we did the Rachel tracking bit, so there I actually showed some examples of if we're in a world where we're allowed to have the first frame labeled, you could imagine if it's a baseball player, you also label the bat. So in some sense, that stuff didn't actually care what was labeled as long as there was, I guess, the synthesized set of poses needed to know that there was a bat there. So I guess it's a little bit hard to ingest that into it. So I guess in the interactive setting where the first frame is labeled, that's a little bit of a cheat, but I think you can try to play these games of having extra objects and have it be part of the synthesized world. The more sort of general recognition problem of, okay, I want to recognize people, and sometimes people hold baths, or sometimes they ride bicycles, and I want to use that as extra cues. Something that I think is interesting about doing this in a data-driven way is that maybe that'll come up organically. So in the same way that maybe it turns out that somewhere internally, one of these filters and these high-level parts is actually reasoning about like a poselet. That's what I showed before. Like, although I wouldn't have had a natural name, maybe it makes sense to reason about a part of an arm and a part of a torso, because that just generates a visually distinctive pattern that allows for easier analysis next layers up. If that happens, maybe it also makes sense to have a part that straddles both a person and a part of a bicycle, in the same way that you have a part that straddles two limbs. So you can almost have poselets that straddle across different types of objects. And this is where I think is sort of the interesting bit where like data-driven latent part learning might help us. It might discover patterns that we wouldn't have naturally thought of, that we might not have a name associated with. And sometimes it's hard to know exactly, well, it is hard to know what the patterns are, but I find that kind of an interesting thought. Maybe the way that we would program these hierarchical parts isn't the most natural way, and it's okay for it to figure out things that would surprise us. Yeah, so I just think that's a neat question. Lots of questions.
Hey, you mentioned in the compositional method that the convolutions with all the templates is your bottlenecks down. You also like doing stuff with graphics. So have you looked at doing the convolutions in your GPUs? Because kind of convolutions in GPUs seem rather meant for each other.
Yes, definitely. So in fact, almost all work now on at least deep learning that uses convolutions uses GPUs. Okay. So it's in some sense, it feels like it's been, if you listen to talks, so I should say I'm not a deep learning person, I'm sort of an outsider, so this is my own view of it, be it right or wrong. But if you listen to talks from folks inside of it, it seems like the fact that they could make use of GPU architectures for parallelized convolution was actually a huge, important phenomenon in allowing those things to work. So I think that's a great point. And sort of like the computational aspect of stuff is, maybe I haven't emphasized that as much as I should, but that's an important consideration that's made these things work.
Just wondering if there's a clear articulation as to where model-based vision went wrong in dealing with the long tail, because it seems to me that you're just kind of adding in back component by component. Only the components are learned this time, and so therefore the components are all running on turbo because they work so well now. And so, yeah, I don't know, where did model-based vision go wrong? Because it seems like it works now, or it seems like to address the long tail, you need these models.
So if the final solution to the long tail is this explicit data synthesis, then model-based vision seems like it fits in so naturally there. We use the models to generate the new version of the data. If this is the final solution, then I think that the place where this can have better answers than the model-based vision thing is this slide. So model-based vision said this is the way to go. And maybe there's actually other stuff that we wouldn't have thought of as better units for reasoning. And so this I could believe. Sometimes, like, for example, like the inverse estimation problem, maybe because occlusion is such a hairy thing to deal with, going from 3D to 2D, the fact that maybe when I put my arm in a certain pose, this negative space, it's a characteristic visual phenomenon. I can model that as a part, which is totally weird to think of from a generative model base. There's no physical thing there, but it's just a visual thing that happens again and again. And that's a useful thing to reason about in this sort of hierarchical processing. And so that would have been hard to hand code.
From the last few questions, it seems to be that you're almost referring to the lack of being able to encode environmental information in these images that you get. So, for example, when you talk about taking a poselet with different objects, say how a bat is held, or how a person sits on a seat, or how a person's foot is in contact with the ground, and that knowledge is something that we don't have any framework to fit it in. And I don't see how much ever knowledge you add. A kid can look at, somebody who's not seen a space flight can look at a person moving in zero gravity and say that's a person and that's a weird environment. And that's something that I don't see zero shot or one shot getting there easily. So incorporating other information about the environment that's more natural to people who are, to even kids, is something that's...
Yeah, so that's a fair point. So maybe there's some things that we shouldn't have to ask these hierarchical latent model to figure out. So physics seems like one. This notion of 3D and 2D occlusions. It seems like these things always have to be true. And why does it have to figure out how to wrestle with it? Can't we, maybe it would really help to have that built in. So I think that's also a really interesting direction of trying to inject that knowledge into this more data-driven view of things.
Okay, why don't we... Okay, one last question, Kevin. You had your hand up for a long time. That's Kevin.
Since you're synthesizing the data from an actual, say, a 3D model, in a general sense, could you also leverage the kind of similar to like computer games engines or physics of bounding boxes, collision detection in real space?
Yeah, I think so. So particularly for oh, I didn't mean to do that. Well, so when I showed like the second part of the talk of doing data synthesis, I was trying to hint at that. I think what I hope to happen is to explore opportunities with graphics folks. It seems like they have the right they've kind of thought about these issues of synthesizing for a long time. And so that makes total sense to me, to push with that agenda. It still goes back to like this question of, but synthesis is still hard, but it'd still be nice to see how far we can go with explicit models on that side. I guess the reason why I like that as a way of introducing models into the story is because that's introducing models in the data generation side, which seems like where our intuitions make sense for generating data. But for the inference side, that's where maybe the intuitions we have don't make sense. But that's where we let the data-driven black boxes do their thing.
Okay, I know some people are leaving. Let's conclude this session here. Anybody has to go away. Let's thank Deva for great depth, all these questions and all these answers.